All right, time for another draftphysics.com, debatephysics.com also. But debates in these little tiny pieces and answered, frankly, claims that, where they could just give me their counter theory and explain how it actually works. What's the mechanism? How does energy work in the universe? Should be sort of something they know because it's basic to physics. It's understanding that kind of stuff. All right, so anyway, simple question is asked in the sense that this relates to the Professor Lewin statement. This is where he made his statement that nature can deal with kinetic energy one way or the other. That is, it can disappear, no problems, but nature can't finagle momentum. It has to do with this spring thing and what springs do. But, okay, the question becomes a little more complicated when you talk in terms of idealizations versus earthbound experiments that have complications like friction and gravity. And so that's how I'll illustrate, I think, a valid point. So there's no, what the hell does that little red thing mean? Remove heart. Yes, please. If a spring launches two objects in opposite directions, do you think the objects must have equal momentum? If you're not on Earth and there's no friction, yes. But it depends on the direction. It depends on the friction that gravity's creating. Okay, there's a force of gravity. And so it complicates the question because it depends on which way if they're moving into a gravitational field or not, then that's going to create resistance to motion, obviously. Or it's going to create extra motion, depending on the circumstance. All right, so we'll try to illustrate this and such. I probably can just do this and get rid of it, right? Yeah, it's what you can do. All right, well, that's a little dark, but it's very clear, so maybe we'll stick with that. All right, so I was thinking about it. I was thinking about the ball bearing experiment. It's not a spring, but, you have this elastic effect where, you drop a ball bearing and it just keeps bouncing and bouncing and bouncing. And there's no energy being lost to some other event. But the thing to understand is the fact that it's falling. All right, so if we have the idealization, and I take a small object and a big object, and it doesn't matter how big it is, and I put a spring between them, all right, the fact is I'll get the same momentum this way, because there's absolutely no resistance to motion, as I'll get this way. So both objects will move. The big object will move proportionally slower, same MV, okay. So obviously one's going to have the very big M and a little v, and the other one's going to have a big V, okay, and a very little m. So that's going to be the distinction between what's going to happen, but they're going to conserve the momentum. All right, so now I change the scenario. So instead of moving horizontally and freely, okay, I change the scenario, and let's make it an object dropping. So now we'll do the anvil in space thing. So I have a big, heavy, hard object, and then I'm going to drop a small object on it. Well, the catch is, if I'm keeping this in one position in space, okay, and it's in gravity, you'd have to apply a force. So there's no way I could keep it in one position, stop it from moving, without applying a force. So if we could agree on that, there's no way to do it, right? I have to apply a force. And the same thing happens on Earth. I have to apply a counter force for something to stay in the same space. There has to be a counter force to the gravity. So it's in gravity and it's being pushed down, okay? And the only way I can keep it from falling down is I'd have to apply an equal counter force. So this object's actually moving, but it's not moving, right? It's obviously it has compensating energy. And the trick is what's this object going to do, right? This is the part that's very interesting to think about. It's absorbing a force that would have hit this object. So if the only momentum this has, that is you dropped it in the gravity, so it only has gravitational energy, you didn't throw it, you just dropped it, then all the energy it has when it falls towards the anvil, right, So it's free to fall. It's free falling. The anvil is stuck because I'm applying a counter force, okay, to keep it going, keep it in one spot, keep it stationary. All right. So all the energy that this object collects as it moves towards the anvil, all of its energy was energy it was going to hit the anvil. That's the simple truth, right? That it's absorbing gravity. The absorbed gravity is no longer now going to hit the object. That's why there's an equal and opposite attraction in gravity. And so essentially it's just going to hit it with a force this is already compensating for. So it's, as this thing falls towards it, this thing is actually getting hit by less gravity, so it starts moving up. And, technically. And so when it hits, it's just going to neutralize that little bit of motion forward, and it's going to move backward again, right? It's going to move back to its original condition because the force that this thing was absorbing and wasn't getting to the anvil. So we know the force is moving the speed of light. The object's moving much slower. So we know that this knows there's something falling towards it before it gets to it. So before it actually hits it, it already knows something's coming. Now that experiment's sort of been demonstrated by that Action Lab guy, in the sense that the impact happens on a surface before the object actually hits the surface. So the gravitational effect is already being has already been absorbed, okay, and in some sense by the fact that the object has absorbed a force that would have affected this object but didn't get to it because this object is absorbing it and it's moving much slower, so the timing's way off. All right, and so that's why you would get this bounce back. So you get the bounce back from the anvil not because the anvil doesn't move, but because the anvil is actually being pushed back up. So on Earth, the fact is there isn't just a force down, there's the force of the Earth pushing back up, okay? And that force is the one that will, as something falls towards the Earth, that force gets stronger because the gravity gets weaker. So that's the interesting part. So if there's something falling towards something falling towards something else on the Earth, the fact is it's absorbing gravity that would have hit this object but didn't. So the object is now buoyant in the sense the Earth has got more pressure. It pushes back up a little, pushes it up a little because the Earth has a constant amount of pressure. This has got less pressure coming down because something's in the way, absorbing the gravity that would have hit this. All right, so it becomes buoyant. All right, so you really have a circumstance where this is coming this way and this is coming this way. All right, except, okay, you can't add the energies because it's all energy that this would have had hit it anyway. All right, so it's basically just saying this never feels the impact because the impact, frankly, is the same as what gravity would have been doing anyway. So it's an irrelevant impact. So this yields, this just reflects with the same energy it had. If they're elastic. Obviously, if something crushes, then you've used the energy. Now, in the circumstance, so you can make this more complicated. Now, this isn't that complicated, really. I mean, this shouldn't challenge anyone who cares about physics and then who has any kind of physical literacy. This shouldn't be too challenging. So now we're going to change the circumstance and say we have an object on a surface. So now it's frictions in the game. So it's not just, okay, gravity, it's now friction. So now you're going to hit something this way, okay, and gravity is going to be irrelevant, obviously, because there's no differential going in this horizontal. There's no gravitational differential in the horizontal direction. It's only in this direction there's a differential. So they have equal forces applied to them. And so what's going to happen in this circumstance is, the people make this argument that I could swing something in and that the Earth will move this other object. So this whole object will move the entire Earth because it's connected. And this object will go this way and this object will reflect, and somehow you haven't made any extra energy. Even though you have twice as much force in the universe now, you didn't make any extra energy. And the argument is, of course, you did. And of course, you're going to use energy to this friction. So this is the key point is that when this hits, it does, okay, impose momentum, but it doesn't move. So the key thing is there's a point where it doesn't move, and if it doesn't move, then there's a complete reflection, okay, because you stopped it from moving. And the point would be is if there was sliding friction, that is, if this moves, this yields, then this is going to bounce back less. So the more this yields, the more this bounces back. But if it doesn't yield, then this friction is tight, and it's not creating any heat. Okay, so the key ingredient is the heat. If something doesn't create heat, then it's not using the energy. That means the bond is stronger and there's no loss of energy. And so basically, the argument is that you're really using the counterforce of gravity again, and it's just changing the direction, just like the pendulum is changing the direction of gravity. If I swing, if I drop something, the force was this way, and I'm changing the force to this direction. Well, gravity's doing the same thing. It's changing this force up into this force sideways, and that's why you get the reflection. So it's much more complicated when you think through all of the permutations. But the fact is if you have motion in this direction, okay, you have used the motion in this direction. You can't create. Again, the experiment they claim they can do is they can put 100 momentum in, and they can get 150 momentum out in this direction. Actually 200, like I said, I explained how you can easily convert that into 200, and in the case where you don't move, where the object doesn't move, you can actually convert it into 300. So you can, not only double your momentum, you can quadruple it, which is irrational, frankly, to the way the universe functions, because there is no free momentum, just like there is no free energy, and energy is momentum, blah, 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 blah. All right. Let's see if the simple question can't be answered if you're going to start talking about carts with wheels, right? So we know that wheels are a problem because they store angular momentum. So you could think you have a certain amount of energy going in a direction, but you really don't, because you have to add up all this rotational energy, okay? And it's invisible because it's circular. So it's not doing anything linear. It's doing something, it's going around in a circle. And you only collect it when you stop this from moving in the right way, where all of the rotational energy ends up pushing in the same direction, okay? So if I hit a round ball, you could think if I hit a round ball into a brick wall, a rolling ball, the problem with that scenario is that you're not going to turn all of the energy into linear motion, because some of the energy is going down, some of the energy is going up, some of the energy is going the way you want, and some of the energy is going the wrong way. Okay, so you know that there's these components, and you know what's going to happen is this ball hits the surface, it's going to end up rising. It's going to end up doing something because of the rotation. So you're not going to get all of the energy in this direction because of the way it's going to move. But if you have an axle, then the axle will transfer the energy going in all those directions into motion in this direction. So the axle will do the transfer of taking energy going in all the wrong directions and pushing it essentially in one direction rather efficiently. So with an axle, the wheel can convert the rotational energy of the wheels into linear motion, a linear momentum. So if you're using carts, obviously you could get very different answers depending on how much mass is on how many wheels. Presuming the same relationship, you're still stuck with the friction coefficient might not be the same. So I don't know if you can't make the argument that no matter how heavy you make the cart, it'll move with the same linear momentum, because the argument would be is now you're going to start heating things. So you won't see the cart move, but it will heat the surface, or it'll heat the gear, or it'll heat the axle, and the energy will be lost in that heat. So it won't look like it moved, but it actually did use the energy. because it made something hot. So friction really has to be understood as having two components. One of them is the contact part, where you're actually trying to move more mass, and the other part is where friction fails and it only agitates or abrades the surface. And if it abrades the surface and causes vibrations and heat, well, then you've used the momentum to do all that little stuff. So it's the same as denting. So you could argue that friction has kind of an elastic friction versus an inelastic friction. You can't just talk about friction as being one thing, because it can manifest in different forms of being strong contact versus weak contact that creates abrasion and basically only heats the surface of the object that you're in contact with. All right, let's see if I can think of any other things to add or restate. All right, so in the category of, boy, I wish science had done these experiments, right? I mean, I wish some scientists had done these simple experiments. So I've used this zip gun as an idea. Now, this is sort of duplicating the spring, you know. And the idea is you could have an explosion here in the middle, and you could put two bullets on either side. All right, and what are you going to get? All right, versus, okay, just one bullet versus a sealed container. So, I mean, we could have those three experiments, you know, and you could just say, well, you know, why isn't this question answered? So let's just say it's sealed. You have your explosion and you have a bullet. All right, and then, you know, these are, let's see how to describe open and sealed. I could just make this a sealed. This is not an opening, okay. And this is an opening. I guess I could make it like this so you can see it's an opening here. These are openings and this is not opened. Does the bullet go out twice as fast, right? I mean, does the energy from the explosion get doubled because it doesn't have anywhere to go on the other side and therefore reflects and pushes the bullet faster? So, you know, yeah, I would say that it's possible that there could be some extra pressure buildup, but the fact is this all moves very quickly, the speed of light kind of stuff, and maybe there's just no time. The bullet's already leaving before this end knows that it's a closed container. Now, we could probably do this with some sort of air experiments, compressed air or something. Obviously, if there's an escape route, then you can't build up any pressure. But an explosion is, you know, like a spring. It just has to do what it's doing. It has to push both ways. So I don't know if you can change that any. All right, so what's the other scenario? Both ends open. One end open. I thought there was a third one. Well, I don't remember it. So yeah, so it's a legitimate question, is how much does it make a difference whether this side moves or this side doesn't move? Does that mean that this goes twice as far? So this is back to the spring argument and my argument that, okay, if I'm pushing one side and the other side yields, okay, then this side can't go as fast as if this side didn't yield, right? So the more this side yields, the more the side you're hitting or pushing on yields, the more energy you get out this way. But that's not what a spring's doing. A spring isn't like something hitting something. A spring is it's pushing both ways, and you really can't undo the fact that it pushed this way. I mean, it can't just automatically. Reversing the direction requires a subtle a mechanism where the timing is the same and it can get the energy in the same direction without losing any time. And that's the question, is that possible in the spring circumstance? So, so this relates to, does the spring push it faster if this thing doesn't move? Now, I'd say, you know, logically you're saying, okay, this is you throw a ball at a wall. If the ball yields, then the ball doesn't come back as far, right? And the less the wall yields, the more spring you get and the more you can get back. Now, tennis balls are only 75% efficient, which is well below what I would have expected. So it's not easy to make something that actually comes back with the same energy you throw in. But ideally, you could understand that, yes, the more the wall yields, the less I get back as a reflection. So obviously the motion of this object is consuming, okay, the energy, the pressure, some portion of it, and that's why you're not getting the full reflection. And the less energy it absorbs, the more energy you get back as a reflection. So, I mean, I think that's consistent. But again, the difference between something that's elastic, because it's hard, and it communicates motion quickly, and elastic in the sense of a spring, which is it doesn't communicate anything quickly. So they're two different things. So you can't use the hard object bounce idea and the spring idea. They're not exactly the same. Now the idea is that a tennis ball is essentially a ball, a hard object with a spring attached. It compresses the spring, the rubber, and increases the air pressure and uses those things to create essentially a spring. So it's like throwing a ball with a spring on it. Yeah. But you can't make more momentum is the argument. You can't ever increase the amount of momentum traveling in any direction. It just doesn't matter what direction is, because as I pointed out, in this simple scenario with the pendulums, that you can swing the pendulum with you can have a little object and apply a force to it. Okay, it can hit the big object. And if you're saying that, okay, I did that, a 1 to 3 relationship, and I now have 150 momentums going this way, well, I can just store that. So when this big object swings up, I can stop it, okay, at its height potential. That'll give me 150 momentum if I let it go. So I can just stop it there, catch it. And then the small object will, because it's swung back this way with 50, okay, momentums, it'll swing back up this way and almost go to this height, but not quite. All right, so I have 50 here in height of the one mass object. So the 3 mass object is here, the 1 mass object is here. Now I let them go together. So now they're right next to each other, and they're going to travel in this direction with 200 momentum. And obviously they'll swing back this way with 200 momentum. So it won't matter the direction. The direction will be irrelevant, because gravity perfectly exchanges, almost perfectly, the energy in direction. So a pendulum's doing a simple conversion just using gravity to change which direction the energy is going in. So obviously directions don't really subtract in any way. It's all momentum. It's all motion in the universe, and that's all you can have is a transfer of motion. And you're transferring it based on the quantity of motion, or its momentum, MV. No squared. Just mass and velocities. That always has to be conserved. Masses and velocities. There's always the same amount of mass and the same amount of velocity total in the universe. The total MV is always the same. All right. So I think that's enough said, right? So a counter question to you is, do you really believe I can put 100 in momentums and I can create a machine that gives me 200 back? 200 in the same direction or 200 in the opposite direction? Doesn't matter. Momentums. Well, I'd say you can't, okay? I'd say that Professor Lewin might answer the question. I might actually say, yeah, you can't. He might actually say it. I don't know. I have to test him on how consistent his own understanding is. And so let's understand, he did pose this as giving you a sleepless night and something he didn't want to directly answer the question. He left it I'll leave this for you to think about. He never really answered the question, frankly, about how it's possible that I could put 200, twice the momentum into an object and get 100 back. Because that is ridiculous, frankly. That's 300 momentum and you only put 100 in. Can't do that. All right. Yeah, so I think that's probably enough. So it's not as simple as, you think it's some simple question. It really is a more complicated question. And you have to test under different circumstances. So again, if you're in the idealness of space and you have a spring, it's not going to matter how big the mass differential is. The spring will do its job. It'll give its half the energy that way and half the energy that way. It'll push both objects. And the question is there, if you could create some sort of friction, some sort of way that one side can't move, is there any such thing? Is there any such way to create any mass too big to move in space? And in space, you could argue, no, there isn't. All right, but in the circumstance of gravity and friction, it's a different question. And because friction can absorb energy, you can convert it into heat. So you can lose the energy without moving the Earth because the anvil slides on the surface of the Earth, some sort of thing like that. So you can burn up the energy without giving anything momentum. Other momentum. I mean, heat is momentum. Heat is little things moving, period. Lots of them. Lots of little elemental movement. And it's the same MV. And you've used the energy that something has when there's heat. All right. Good enough. Yeah, well, maybe I'll pause. Like I said, it's a deep subject. All right, maybe I just work on clarifying the point about the idea of a bazooka. Okay, so a bazooka is going to shoot something, and it's just basically a tube, and you put a rocket inside of it, okay, and there's nothing for the rocket to push on. So the fact is that all the exhaust is free to leave, and there's very little recoil. Okay, I'm not going to say very little. I mean, obviously there's a whole bunch of force hitting these surfaces, so they're going to collect some of the energy. So you're going to feel something, and then the rocket shoots out. And the question is, would the rocket shoot out any better if this end was sealed, okay, and it was a mortar instead, you know? So mortars are just doing something different in the sense that, well, actually they're grenade launchers, so they don't really, you know, they are basically using a spring device to launch a grenade. So that is completely different because there's no exhaust. All right, so you have to think of some other way to explain the circumstance. But yeah, so the simple question is, if I sealed the end of the no, I forgot the name of the damn thing. Yeah, it's just so funny. Getting old is just so interesting, you know. But yeah, this stuff just disappears, and you're saying, wait, where did that go? I mean, So this bazooka, there we go, bazooka. Okay, if I sealed the end of the bazooka, obviously now it's going to have a ton of recoil, okay, because all of this exhaust gas, I'm not letting it out in that direction. So it's going to be a real force that I'm going to have to, you know, secure myself. It's like a cannon now, okay. And but does it make any difference? And that's the question: is does it make any difference? Obviously, for guns, the reason why they seal the end of the gun, part of the reason is you don't want all this shit blowing back in your face. So it's better to have it go out some other way. And then they use now, you know, the modern technology, they're sealing the combustion chamber more and more and using that torque, the energy created, to, you know, shoot the shell out and reload another shell and all that kind of crap. So obviously the recoil is being grabbed for the very purpose of doing work. But does that make the bullet leave any faster is the question. And, you know, my answer is no, that you're not going to get a higher velocity out of the bullet because the explosion is too fast and you can't reverse its direction fast enough to add momentum to the small bullet. The bullet's already traveling away from the explosion so quickly that you can't wait for a reflection. The bullet's already moving away. The reflection can't catch up. That's the problem. All right, anyway. That's probably enough now. So, simple question, and there frankly isn't a simple answer, because there are different circumstances. So in the idealization of space, a spring will push in both directions with the same force. It'll go push big things slowly and push little things quickly. Now, the point is the spring has a maximum capacity, its own velocity. So if you put something really, really light in front of the spring, you won't gain anything because the spring can't go any faster than it can go. And so it won't be able to push the lighter thing faster than the spring can move. So you can't put a piece of dust on a spring and expect the dust to fly off at some supersonic speed, because it can only go as fast as the spring is going. Alright, so till the next time as such, that should be enough. And so forth and whatnot.